Hi, welcome back. In any structure, there are fundamental building blocks that are used to create the system, whether it be columns and beams or slabs. To this point, we focus mainly on the design and analysis of beams. Today, we're going to turn our attention to types of concrete slabs and how to design a certain type of them, in particular one-way slabs. So without further ado, let's get started. In a structural system, there are two types of slabs that we're concerned with, and they have very simple, straightforward names. The first one, and the one that we're going to be covering in this lesson, is called as a one-way slab. And basically what this is this is a slab in which bending is occurring primarily in only one direction. Now, idealized, what that means is that you have something like two walls, that run parallel to each other, and then the slab spans between them. So the only flexion that can occur in the slab due to a load on this is it will only deflect in this direction. Okay, so that's one of the constraints. If I have that scenario, I know I have a one-way slab. However, there are scenarios in structures in which I don't have that situation, such as maybe I have a slab that instead of being supported fully along two edges, maybe I'm only picking it up at at 4 corners, at the corner locations. And so in that problem, depending on the spans of these things, the moments that are present may occur not only in this direction, but you might get one over in this direction. Again, this wall isn't here. We're now replacing that with some sort of vertical support, and then it wants to span that direction. Okay, when it bends like that, that's called as a two-way slab. Okay, so if I have, so if it's a perfectly square slab, then I clearly get bending in two directions. But what if it's longer in one direction and shorter in another? Okay, well, in those cases, we can start to say that that's one-way behavior, but we've got to be a little bit more careful about it, okay? So what we can do, in the way the ACI code sets us up, the one-way slab provisions are located in ACI 318.19, Chapter 7, up toward the front of the book. In the structural elements, and then there are requirements scattered throughout, which I'll try to point out in this video. So if we look though, the way that we're going to define this is that let's call L as the span of the beam and B as being the other dimension. Okay, so if we take and we look at the situation where the larger of L or B were what we call the longest side, if that number divided by the shorter of the two sides, oops, left off T. It's got that in there. Okay, if that value is greater than 2.0, this is still considered as one way. Okay, so it's a 2.0 ratio of the longest side to the shortest side in situations where I'm not being supported fully by a wall or continuous support. Okay, all right, so we kind of talked about that. So two-way slabs, bending is typically in two directions, typically supported on 4 corners. Okay, now the advantage of this, they're a lot more complex to analyze, but there are a lot more behaviors that are occurring that you'll cover in an advanced concrete class or in graduate school. In typically an undergraduate class, we don't cover two-way slabs. But one thing to realize is that they are harder to design, but often they result in thinner slabs, okay? But the calculations and the details are a lot more involved. Okay, you have to be very careful about where you put steel and the directions and the orientations of them, and it becomes a little messy, but you do get some economic savings when doing it. That being said, as we're first exploring the concept of slabs and trying to step into understanding the basic behaviors, we've got to get our head wrapped around just what is a slab and what is it doing from a one-way perspective to even be able to begin to understand the two-way direction. Okay, so that's what we're going to do. All right, so okay, so a couple of provisions that we have to consider. Okay, and some of these you've seen before, but they're a little bit different for slab versions as opposed to the beams that we studied back with the SRR calcs and the DRR calcs. If you need a refresher on those, go back and look at those videos on SRR and DRR and the design and practical considerations videos that we did on those. The cover requirements for a slab come out of ACI 20.5.1.3. And they say that for slabs that are not exposed to weather with a number 11 or smaller bar, the cover is typically 3/4 of an inch. Now what you're going to find that for most one-way slabs, the bar sizes are generally fairly small. You'll be seeing things like a number 3, number 4, number 5, number 6 for a normal building, a normal construction scenario. So that kind of works out pretty well. All right, so a cover of 3/4 inch on these smaller bars is not a big deal. It still gives you about a 1 inch from the center of the bar out to the outer fiber of this thing. So this is a little bit different. This comes out of that same table where for beams we were seeing covers of 1.5 or 2 for flexural members, but slabs are a little bit different. Most slabs that we're going to consider are almost always not exposed to the weather. They are at the interior of a building that is sealed off from the elements. We're not looking at doing things like bridge deck slabs or those kind of things. So the design is similar, the cover requirements would be different for that guy just because of the presence of the elements and whatnot. Okay, the other provision you've also seen before, okay, and this is a minimum thickness, okay, and this is going to be called as HMIN throughout this video and in your textbook. Okay, this comes out of ACI 7.3.1, okay, and it assumes that FY is 60 KSI. For any other steel grade, you have to do a correction to these dimensions that you can read up on the code yourself, but for most practical purposes, we're safe to assume 60 KSI. Okay, if the beam is simply supported, HMIN has to be greater than the span over 20, that L dimension that we showed you in the last picture. Okay, if one end of the beam is continuous and the other is not, then HMIN is L over 24. And if both ends are continuous, and so this would be an interior span on an interior beam of a continuous system, then your HMIN would be greater than L over 28. Okay, so you can see that as you get more and more continuous, the thickness that is required gets smaller and smaller. Okay, all right, now, assumptions that we're going to make in the design of these one-way slabs. Okay, we're going to make a couple of assumptions on this, okay, because one of the problems that we have with slabs is that the dimensions for the span, that L dimension and that B dimension that we showed back on that first page, if I pull that back up here so you can see it, these dimensions, is that these guys can be very, very long, okay? And so what we usually do is we look at taking a tributary width or a unit width slice out of the slab and designing that and then replicating it the rest of the direction. So for us, we're going to assume that it's a 1 foot wide strip that, and basically design it similar to what we did for beam design, okay? So the first assumption we got to do is we got to assume a phi value, right? So just like before, we're going to take a guess on this. For slabs, typically it's pretty safe to assume phi is 0.9, but we do have to check it. Okay, and you check it the exact same way that you did the SR. You got to go find the strains and verify that it's, where is it in relation to that 0.005 number for 60 KSI steel. Okay. For higher grade steels, you have to do something a little bit differently, but again, that's beyond the scope of this class. For the second assumption, we're going to assume that the width B is 12 inches. Even though the big B may be 30 feet, we're only going to look at a 1 foot wide slice of this thing. Our depth of our section, H, is going to be the H minimum from the table that we just talked about. The ones I outlined up here, these are actually in a table in the ACI code at 7.3.1. Okay, and then the nominal moment, Mn, is going to be equal to the factored moment divided by phi. Okay, all right, so let's talk about how you use this information to find the steel areas. Okay, so a couple of things to consider. There, in any slab, there will be steel running in both directions. We're going to start off with what we call the main steel. So that same picture replicated, if I have a span of L, okay, the main reinforcement is assumed to be running parallel to the span, okay? It's the longitudinal bars, if you will, on this particular section. Okay, so they run this way. Okay, and so those are the ones that are being used for strength, and they will be, and that's how we're going to calculate those, okay? So it runs parallel to the span. We calculate things in terms of a reinforcement ratio for the main portion, because again, we're not looking for a total area of steel, although I guess we could by taking a 12-inch width. But if we look at the reinforcement ratio on this, the formula is 0.85 F prime C over Fy multiplied by 1 minus the square root of 1 minus 2 times the nominal moment divided by 0.85 F prime C BD squared. So be really, really careful in calculating this, that it uses a nominal moment, not a factored moment here. Okay, and then we also use the depth of the beam for us. So for us, we're going to assume that typically that the depth is, D is going to be H minus 1 inch. And we'll talk a little bit more about that here in a second. Okay, so that's the reinforcement required for strength, because we've got the applied moment involved in this. Okay, there is a minimum reinforcement ratio that's located in 7.6.1.1. Okay, and it basically says that rho min is going to be equal to the value of 0.0018. Okay, the reinforcement ratio. Or we could calculate that as an area by taking that number and multiplying it by B and then times D, where B is 12 and D is H minus 1. Okay, now this turns out to be the minimum amount required for any sort of thermal resistance. So if your strength is so low, your requirements for strength are so low that you don't meet this number, they're going to make you bump up to this just to prevent shrinkage cracking on this. So that's your minimum value. Okay, a couple other things for the main reinforcing that we need to look at. We have our minimum bar spacing. Okay, that's located, you've seen this one before. This is over in ACI 25.2 or 25.2. We covered this earlier. Okay, and the minimum spacing is the maximum value of either 1 inch, the bar diameter, or 4/3 of the max aggregate size. So again, you've seen that before. Okay, the max spacing is located in 7.7.2.3, and for the main steel, it is the lesser of 3 times the slab thickness or 18 inches. Okay, so you're not allowed to space bars any further than 18 inches from each other in a slab. Okay, so depending on what your H is, for smaller H's you actually have a smaller max spacing, but for larger slabs you're bounded by the 18 inches on that. All right, so that's for the longitudinal steel. Okay, the second set of steel that we look at is what we call the temperature steel or the transverse steel. Okay, so even though the strength of the slab is, and I've put this 12-inch width of our design element where the longitudinal bars were running this way in the last photo, the temperature steel runs perpendicular to that. Okay, and that's the orientation of our temperature steel. Okay, now as we look at how steel gets placed in the cross section, one thing that we got to be really careful of is that if this is my H, okay, and we're looking at a 12-inch wide width, okay, the main steel needs to always go on the bottom. Okay, for when the main reinforcing is on the bottom. Okay, when the main reinforcing is in the top, such as going over a continuous support, this temperature steel goes below it. Okay, and part of that is because if you think about this location here, you know, if I maintain my cover, that's pretty easy to monitor. Okay, this would be my D from the top down to the center line of the bar. But if for some reason these got installed backwards where the temperature steel got put in first for the bottom bars, this distance would be decreased rather significantly, because again, the thicknesses of slabs are usually like 6 inches, 8 inches, 10 inches. They're not real big. It's not like beams where if we were off by an inch or two, you know, and got bars flipped around, our D was still fine. Here we can get a large percentage increase in that just by getting these bars put in the wrong order. So we want to make sure that we get the main steel as far down in the section as possible while still preserving this cover thickness. Okay, and then the temperature steel in this case would go over the top. Okay, for the top steel, that's my main bar. Then the temperature steel will go on the bottom. Okay, underneath it. And again, that's because my D would go from the bottom up to the center of that bar. I want as big a D as I can to help me with the strength requirement for those. Okay. Okay, so this is what we call being placed to the interior of the beam. Okay, it's not always on top and it's not always on bottom. It depends on those. So that's why we're saying it's more toward the middle of the bar here. Okay, basically above the bottom bars and below the top bars. So that's kind of a constructability system. This also illustrates that you've got to be really sure with your quality control program that the people that are installing these put the bars in the right direction and at the right location. So you've got to always keep your eye on that, because they can steal as much as, depending on the size of the bars, 7, 8, 9, 10% of your strength by putting these things in backwards. Okay. Now, in some cases, if you don't trust the people that are doing the work, I guess you could assume that it's always on top, okay, and then design for the D that's there, and then when they put it in the right spot, you're pleasantly surprised. But typically, that's not how it's done, and it's generally not a problem, but you do have to be conscious of the placement of these bars, because there's so much steel going on in these cross sections. Okay, like before, we do have a minimum reinforcing ratio. Rho min is again 0.0018, but now for the temperature steel, the area of steel is going to be this 0.0018 times B times H. Okay, so the difference is here. Before it was D, now it's H on this guy, and that's the only other difference, really. Okay, the minimum bar spacing, same game that we played before, 1 inch, dB, and 4/3. You take the maximum of those two, that's your minimum. And then the max spacing is a little bit different. You find this in 7.7.2.4. It's 5 times H. Before, remember with the main bars, it was 3. Now it's 5 times H. And 18 inches. Okay, and what this steel does is the reinforcing steel on this is basically used for to provide resistance for thermal effects or for shrinkage cracking. Okay, that I need a minimum amount of steel to kind of hold things together to keep those cracks from growing too large. Okay, and so this is how we do that. Okay, now what I've got here is a design aid, and this will be included in the packet that you download. I whipped this up on Excel pretty quickly because one of the things that we want to be able to do is quickly determine, if I can do my row calculations, turning that into a bar size at a particular spacing becomes a little bit more difficult. So what I've created here is a one-way slab design aid for a reinforcement ratio per foot. Okay, and that per foot is important because we've assumed a 12-inch wide section in our analysis. Okay, and so if I do that, if you kind of look at it, so if I put one number 9 bar, we know that the number 9 is 1 inch squared, okay, and I put it at a 12-inch spacing down here, you can see that that value is 1.0, that it would be, that we would have a single number 9, okay, for at 12 inches. So my reinforcement ratio for him would be 1.00. Whereas if I put my number 9s at, say, 3 inches on here, then this is, now my reinforcement ratio is 4.0. So all we have to do is calculate our row values, and we can quickly come down and we can pull off the spacing that gets me the minimum row value that we have to do. It's a pretty easy table to build. It took me about, I think, 10 minutes with formatting to get things looking nice to be able to whip this up. And so now I've got it forever. But it's a pretty easy design aid to be able to do. Whereas we know that for a number 3 bar, okay, that its area is 0.11, and there are 4 3-inch spacings per foot. So it's basically my area of steel times 12 divided by this number gets me the number that's here. All right, so if I write this down a little bit just so you have it, is that our number is going to be, rho is going to be equal to our area of our bar, okay, multiplied by 12 divided by the spacing. That's the calculation that I did. So for all the different bars I plugged in, 0.11 for number 3, 0.2 for number 4, and so on here, and then I multiplied that by 12 and I divided by the spacing. That gets me the reinforcement ratio that we're looking for. Okay, and so that's kind of, and we'll use this when we do the design example here in a moment. But it's a pretty handy tool, and like I say, this is in your packet, and if you want to take it with you, and I used to have one years ago when I was doing consulting work. I had this table laid up or pinned up on the side of my cubicle because I used it quite a bit for doing quick slab stuff. I could do the strength calculation very quickly, and then this helped me with the detailing and really expedited the process. But again, all I was doing was this calculation. I just didn't want to have to punch it in every time. Okay, all right. Okay, all right, so here, let's take a look at an example of one. Fairly straightforward. Okay, we're going to do a one-way slab design example. It's going to have a span of 15 feet. Okay, our F prime C is 4,000, our Fy is 60 KSI. We're going to put 150 pounds per square foot over the entire area of this, and our dead load is going to be just the self-weight only. Okay, our cover then is going to be equal to, okay. So as we said before, our cover amount was 1 inch. Basically, the depth of the beam was going to be equal to D plus 1 inch. Now again, we said 3/4, but this was because the depth is measured to the center of the bar and the cover is measured to the edge of the bar. Okay, so that's why this 1 inch, and it works for smaller bars. Okay, all right. So if we kind of look at it, we're getting kind of a sketch of something that kind of looks like this. Okay, so my D goes to the center of the bars, my H is the full depth. We're doing a width of 12 inches as we assumed, and my main bar is on bottom, temperature steel on top. Okay, so how do we compute this? So the first thing we have to do is we got to figure out what is our factored moment. Okay, so we were given that there was 150 PSF applied. Okay, so getting our values, B is 12, we said that, H equals H min. For simply supported, that was L over 20, so this is 15 feet times 12 divided by 20 gets me 9 inches. Okay, so my D for this beam then is going to be equal to H minus 1 inch, or 8 inches on this. Okay, the dead load here, WD, is going to be the density of the concrete, and we said it was normal weight, so that's 150 PCF. Okay, and I'm going to convert that to kips, divided by 1,000. My B is 12 inches. Okay, and my H is going to be 9 inches. So those are my two values that are happening here. Okay, and there shouldn't be, there's no units on that. It's not per foot. Okay, all right, and so that number gets me a weight of 0.1125 KLF, or about 113 pounds per foot for the dead load. The live load we said was 150 PSF, okay, divided by 1,000 to get to kips again. Okay, and now we're going to multiply that by the unit width of the slab, 12 inches, and then I'm going to divide it back out by 12 when I convert to feet. All right, and so that's one of the reasons we like doing that 12-inch width, is that it cancels a lot of these conversions that we have to do. Okay, and so then my weight for the live load is then 150 pounds per foot, or 0.15 KLF. Okay, from there I go and I do my factored loads. Okay, so I'm going to do 1.2 times WD plus 1.6 times WL, and if I plug those numbers in that we just calculated, I get basically 375 pounds per foot, or 0.375 KLF. And from this, now that that's a factored load, I can calculate my factored moment, which is WUL squared over 8. This is the equation for a moment for a simple supported span. So here's my W, my L squared, and my 8, and if I do that, my moment then is 10.54 kip feet, and that's per foot of width. Okay, so because again, we're only looking at a 12-inch wide section. Okay. All right, so now we're up to now computing our required MN, because we need MN, not MU. Okay, so again, we're going to assume phi of 0.9. Okay, my MN required then is MU over phi, so and then I'm going to convert that to kip inches by multiplying by 12, so I have 140.5 kip inches is my nominal moment. Okay, so now we go in and we say, well, we're going to compute the required rho. Okay, so this is the main steel calculation. All right, so my rho for my main, I said rho min, it's not really rho min. It's kind of the minimum amount of steel that we need. So it's, yeah, let's just take the min off of here. And we'll do our min. It'll look something kind of like that. Okay, so here's my formula. It's pretty much just a plug and chug value. And wow, that should be an 8.5. Okay, the calculation is right. I just wrote the wrong number down. Okay, 0.85 times 4 divided by 60, so forth and so on. And so your rho required for strength is 0.00310. Okay. Now, once we go with, now that I've got my design rho, now we can go in and we can start calculating our required steel areas. Okay, so my main bars on this, you know, for an AS prime required, or sorry, an AS required is rho times BD. So I'm going to multiply this by 12. I'm going to multiply this by D, which is 8, and that gets me, you know, 0.300 inches squared per foot of slab. Okay, and so then my temperature bars are going to be my my temperature steel. We said was the amount was going to be 0.0018 B times H. I plug that in, and I get 0.1944 per foot of slab. So now we're going to select our reinforcement. Okay, let's take a look at our maximum spacings, because that we'll need that. So S max is the minimum of 3 times H, or 18 inches. So that's the minimum of 27 or 18. So our max spacing for the main steel is 18 inches. And our temperature steel, our S max, is a minimum of 5 times H, or 18 inches. So it's a minimum of 45 or 18 inches is the value. So it's 18 inches is the maximum spacing in both directions for our reinforcing. Okay, now this is how we select the sizes. Okay, we go back to our design aid and look at these amounts. Okay, and so if this is my reinforcement ratio per foot on this thing, okay, all we're looking for is, we're coming into this first one, let's slide this down a little bit. Okay, that we're trying to find a rho required of 0.300 inches squared. So if we go to our table, all I'm doing is I'm looking for values that are greater than 0.300. So if I start with the number 3s, you can see that 0.300, this is the first one that is above. So we would put number 3s at 4 inches would be my first option. Okay, and that's the one that I wrote. And we can continue writing these down. Number 4 is more area steel, so the spacing can be larger, and so the spacing increases down to 8 inches. Okay, and we can continue doing this for number 5, come down, we're down here at 12 inches, and then number 6 actually fits in at 17 inches. Okay, once I get to the number 7s on here, we're sitting at this one, you can see that now we're off the chart, because we're bounded by this maximum value. So that's why I didn't bother writing anything larger than that. Okay, so basically you go and we're going to choose the one that's the farthest down here, because that's the fewest number of bars. Okay, so if we look, this is my table data. So the 3 is at 4, 4 is at 7.5, and then set number 7's exceeded the S max of 18 inches. Okay, so it's one of these would be my options. So you have your option of putting in, you know, a whole bunch of number 3s or a whole lot less than number 6s if I space them at 17 inches. In fact, it's almost 4 to 1 on this, that for every one of these you'd have to put 4 of these in. So that's a lot in your labor costs on this, and so that's why we're going to choose to go to a number 6. Okay, so we have a 9-inch slab with number 6s as our main reinforcing at 17 inches on center. Okay, for a slab, that's a pretty heavy steel requirement. It's a very thick slab based on the dimensions and the weight that we had on this. Okay, so that's how we chose the largest, chose our size. The largest size with a spacing less than S max, okay? And that's because it was easier to install, less work required. So that's our selection for the main steel. Okay, we'll go in and we'll do our temperature steel. Okay, so same game. So my row required is 0.1944. And again, we're using the row values because one of them used D in the main reinforcing and the other one was using an H, okay? But we can come in and look at our temperature steel and we go back, and if I convert it to row, then the table works for both. Okay, so our row value is 0.1944, so we're going to play the exact same game. Number 3, we come down. I'm looking here at 0.2 is the first one larger, so that's at 6.5 inches. Okay, if I come down to number 4 and I'm looking for a 0.20, we're now at 12 inches. Okay, and if I go to number 5, you can see we're off the chart. Okay, if we come all the way down to the bottom of this row. Or I could say 18 inches, but it's, you know, more than likely we're off the chart. Okay, so that's what we're going to do there. All right, and so those are the sizes for what we have happening here. So 3's at 6.5 or 4's at 12 are my options for this. So we're going to choose the one that's larger. So we're going to take 4's at 12. Okay, and then we need to provide kind of a preliminary sketch for what we're doing here. So here's my slab, my slab depth. It's 9 inches thick. Okay, I have a cover requirement on the main bars of 3/4 of an inch. Okay, and then each of these bars is spaced at 17 inches, and these are number 6s. And then the temperature steel lays across the top, and those are number 4s, and those are spaced at 12 inches. Okay, now, this was just kind of the preliminary detailing. You do still need to remember to go back and check phi. I didn't do that in this example because I just wanted to focus mainly on the slab, but you've got to check your strains to make sure that you have a tensile fit, a tension controls situation, and so that phi would be 0.9, which for most slabs that's typically the case, but you do need to check it and to verify, so make sure you do that as well. Okay, so anyway, for a preliminary design, that's really all there is to it. It's pretty straightforward. The design aid, the table, is really helpful, but it's also something you can make on your own if you don't have access to the files. But other than that, I think that about covers what we're going to do with as far as one-way slabs. One-way slabs are very important in structures. I mean, they provide our surface for for our desks and our for walking across and whatnot. For concrete structures, and so it's important that we understand this. Now, again, there are two-way slabs out there, and if you take an advanced design class or you go to graduate school, you'll definitely cover them there. But for purposes of our course, we're not going to cover the two-way slabs. But you do need to be aware that they exist and what the limitations are for when we have them. So anyway, hope that was pretty clear for you. If you got any questions, as always, please leave a comment down below, and we'll try to address those as best we can. And if you found the video to be helpful, please like or subscribe to the channel, and we will see you guys next time. Happy engineering.